Hello, welcome to my talk. I'm Krisztian Palotas, a senior researcher from Hungary, and I will talk about magnetic skyrmions probed by spin-polarized STM. Our work was motivated by experiments from Wigner's group, where they showed that it's possible to create and delete magnetic skyrmions individually by current pulses applied on the tip of the scanning tunneling microscope, and we would like to understand its microscopic mechanism, how this works with the spin dynamics and spin transfer. So first we need magnetic structures, and for that we need a classical spin Hamiltonian, what we use, where we have two spin interactions with tensorial exchange, on-site anisotropy and Zeeman energy. This Hamiltonian is parameterized from first principles calculations using this relativistic torque method, and once we have these parameters from DFT, then we apply spin dynamics at zero temperature, the usual Landau-Lifshitz-Gilbert equation, and we can find the ground states of the system. So we arrive at some skyrmionic states, which can be characterized by the topological charge with the well-known formula here. And we can also calculate their spin-polarized STM images using this tunneling current formula, where we have a transmission function and we have some electronic structure component here. So this corresponds to a scalar charge current, and we also generalize this electron transport theory to include vector spin transport in a consistent way together with the charge current. For that, I would like to show you the next slide. So these list the quantities what we can calculate. The charge current was shown in the previous slide. We can calculate longitudinal spin current, which is acting on the tip and the sample, and in-plane components of the spin transfer torque vectors, again acting on the tip and the sample. They have different electronic components, and then out-of-plane spin transfer torque vector. And the total spin transfer torque vectors basically depend on the bias voltage or the tunneling direction, whether the out-of-plane and in-plane components, how can they be added or subtracted. We applied this theory on skyrmions, which have different topological charges. We could stabilize these systems. The details are shown in this paper here. And with an out-of-plane magnetized tip, we find distinguished contrasts, which correspond to the skyrmion symmetry. We find the cylindrical symmetry for the normal skyrmion, and for a higher order skyrmions and anti-skyrmions, we find this C1 plus Q absolute value symmetry. If we check, if we calculate STM images with an in-plane magnetized tip, then we can get more information on the topology. So basically, for the depending on the topological charge, we find the equal number of the absolute value of the topological charge of bright and dark contrast regions. So here 1 and 1, 1, 1, 2, 2, 2, 2, and 3, 3. And for this special chimera skyrmion, which one side is a skyrmion, the other side is an anti-skyrmion, the topological charge is 0. We find an unequal number of bright and dark regions. We can get more information on the topology if we apply in the simulations that we rotate the in-plane magnetized tip. So this was proposed by Bertrand Dupuy in this paper here, and they found that the skyrmion, in the skyrmion, we find an in-phase rotation with the tip magnetization and the anti-phase rotation for the anti-skyrmion. We find the same, of course. It's a good agreement with their paper. But we can also check what happens if this topological charge absolute value is not equal to 1. So therefore we check this sequence of images here for Q equal 2 and minus 2 and Q equal minus 3. So what we find, that for the negative Q, we have the same direction of the rotation of the contrast features with the tip rotation, and for the positive Q, then we have an opposite direction of the rotation of the contrast features. And for the chimeral skyrmion, we find that the two sides, the skyrmionic and the anti-skyrmionic side, they have an opposite rotation, and this corresponds also to this kind of positive and negative values here. So what is interesting, that we find that the angular velocity of the contrast features is directly proportional to the inverse of the topological charge density. So this is illustrated here. So for this case, you see that it has a positive and negative components, and this corresponds to the rotation direction of the contrast. And for the other cases, the speed, so-called the velocity of these contrast features, depends very much on the value of the local Q here. For example, visible here for this Q equal minus 2Ks. So if we switch to the spin transport properties, then we can calculate the longitudinal spin current. So in this case, with the out of plane and in-plane magnetized tip in the two rows, and in this case, this is acting on the tip, and in the other side, it's acting on the skyrmion spins. So what we find, basically, the longitudinal spin current contrast absolute value, the size of this quantity has the same contrast as for the charge current. So once we know the normal STM images, we can already estimate somehow this longitudinal spin current vectors once we know the spin structure here. So this is illustrated. Okay, these are calculated for these 6 different skyrmions here, just to show you briefly. And we obtain again different quantities, which is acting on the tip side and on the sample spins. And if we want to calculate the spin transfer torque, then we know that it's proportional to the sinus of the local angle between the tip magnetization and the local spin of the skyrmion. And this spin transfer torque minimum is found where the current has maxima or minima. So this is illustrated here. So these are the STM images. These are the spin transfer torque absolute values. And once we calculate these, we can calculate the spin transfer torque vectors as well, their components. This is the out of plane component, in plane component acting on the tip. This is the same. The out of plane component is the same. This is acting on the sample, and you can combine them depending on the tunneling direction. You can get different types of spin transfer torque vectors. We calculate these quantities, and we want to use it in the future in spin dynamics to get microscopic insights to the skyrmion creation and annihilation, as I explained you in the motivation slide. It's very interesting also that these spin transfer torque vectors can be tuned or can be tailored basically by selecting the spin polarization of the sample and the tip. So this just shows you an illustration that you can obtain different kinds of STT vectors here depending on the tip sample spin polarization combinations. And for the 6 skyrmions, we can calculate these components again, all these components of the spin transfer torque, and we can combine them to get the total torque for out of plane, and in this case for the in-plane magnetized tip. And finally, we studied this so-called spin transfer torque efficiency, which is nothing else but the torque divided by the current, depending on the tip position for these 6 skyrmions with the out of plane and in-plane magnetized tips. And what we find that the spin transfer torque efficiency can be very large. So here the blue shows the minimum, which is 0, and the red shows the maximal values, close to 25 millielectron volt per microampere. and this corresponds to close to 1 H over E. This is the largest theoretical value that can be achieved. So basically, depending on the tip position where we place the tip above these objects, we can get larger torque efficiency, depending on the skyrmionic structure and also on the lateral position of the tip. So this is what was shown in this paper here. And with this, I would like to summarize. So we use this 3D WKB method for STM, STS, and STT simulation. So we can image complex non-collinear surface magnetic structures. We can consider the tip electronic structure. We can consider orbital dependent tunneling and arbitrary tip orientation. We can calculate the spin transfer torque and the longitudinal spin current vectors. We can combine it easily with any electronic structure code. We can also combine different levels of electronic structure methods for the tip and the surface. It's computationally inexpensive, it's very fast, and we can treat large surface areas even well above 10,000 atoms. And we can use statistical analysis of the tip with this method. And there is, of course, work in progress. We further develop electron charge and spin tunneling theories going beyond this simple model. So we want to go beyond the scalar charge current. We want to include vector spin transport, and we want to feed these calculated spin transfer torques to atomistic spin dynamics calculations to understand this skyrmion creation and annihilation with the tip. And with this, I just summarize, I show you these papers where my talk was based on, and I would like to thank my funding, and I would like to thank you for your kind attention.